So dissociative electron attachment occurs when you have a free electron colliding with a molecule, and that molecule forms a transient intermediate negative ion. And that ion can then dissociate, forming, let's see, sorry, the pointer here. Oh, there we go. And that ion can dissociate to form a that intermediate can dissociate to form a negative ion and a neutral fragment. All right. Now, upon dissociation of that intermediate, energy is released. And that energy can appear as translational energy of the fragments, or it can appear as internal excitation of the fragments' vibrational modes. Now, how this energy is distributed and how long these intermediates last are very interesting questions. So typically, these systems are probed using time-of-flight spectroscopy, using capture of free electrons, either using the electron beam or the electron swarm method. However, as we'll show, we've discovered a way, at least in the thermal regime, of using electron transfer through capture with Rydberg atoms to probe these systems. So when collisions are occurring with Rydberg atoms, they're typically discussed using what's called the essentially free electron model, which goes that since the size of an atom scales as n squared, when you have a Rydberg atom colliding with an electron attaching target, the range of interactions between the electron and the target and the core ion and the target are smaller than the size of the atom. As a result, the atom can be considered a low-energy electron trap, and the interaction can be considered a binary interaction between the electron and the target. So obviously, in this case, for very high-N atoms, you're going to get usually just the products are just going to be two free ions. However, with lower N, as the electron cloud decreases, the Coulomb interactions between the product ions become more and more significant. In the extreme cases, you can get a pair of bound ions orbiting each other. This system is called a heavy Rydberg state because a lot of its properties parallel those of Rydberg atoms. Now, because these ions are so weakly bound that then the distribution of ion pairs that remain bound will be influenced by the energy released upon dissociation of the intermediate. We can exploit this fact to learn about the decay energetics of the intermediate and their lifetimes by collecting velocity distributions of the ion pairs that remain bound. So here's our apparatus here. It's anisotropic, so I have a side view and a top view. So to begin with, we have a beam of potassium atoms entering a gas cell where they're photoexcited to a Rydberg state by a pulsed laser. Now, these Rydberg atoms then undergo collisional destruction by colliding with an ambient electron attaching target gas to form a bound ion pair state. Now, some of these bound ion pairs will have trajectories that will allow them to exit the gas cell through a slit here to enter an analysis region, which is basically just a bunch of concentric fine mesh grids. Now, after a predetermined delay time following the end of the laser pulse, a 5 kilovolt per centimeter electric field is applied across these grids here, which can dissociate the ion pairs and propel the positive potassium ions down to a position-sensitive detector where they're collected. Now, by repeating this experiment over many laser pulses, you can get a distribution of positions of these potassium ions and, by extension, a position distribution of the original bound ion pairs. And we can, to analyze these distributions, we can compare them to distributions calculated using a Monte Carlo collision code, which simulates the initial velocities of the atom and the target molecule, the collision between them, and the subsequent dissociation of the intermediate, and the final trajectory of the ion pairs. So first we have a Rydberg atom. We simulate a Rydberg atom colliding with a target molecule, and the initial velocities of these are taken from the appropriate distributions. Now, in keeping with the essentially free electron model, we treat the interaction between the molecule and the atom as a binary interaction between the electron and the molecule. So in that case, with that being in mind, we can just treat the probability of electron capture to just be proportional to the local probability density of the electron, which is just psi squared. So following collision, the trajectories of the subsequent ion pair are calculated classically up until a time equal to the assumed lifetime of the intermediate, at which point the intermediate dissociates and the energy imparted to the fragments is imparted to the fragments according to some distribution that we assume for the translation energy release. Now, following this dissociation, if the ion pair remains bound, their final velocities, their final trajectory is calculated so that we can get a distribution of their velocities as a function of delay time following the end of the laser pulse, the assumed lifetime of the intermediate, and the decay energetics. So the first target we tried this method with was CF3I. Now, upon collision with a Rydberg atom, CF3I forms a CF3I minus intermediate, which then dissociates to form an I minus ion and a neutral CF3. Now, the excess energy produced by this reaction is given by this equation here, where you have the electron affinity of iodine minus the dissociation energy of the CF3I bond plus any internal energy in the molecule plus the kinetic energy of the electron. Now, these values sum up to about 0.7 eV. Now, where does this energy go? Well, a lot of that depends on the lifetime of the intermediate. If the lifetime of the intermediate is very short, as in the electron is captured by an anti-bonding orbital, then nearly all of that energy is going to appear in translation, and the translational energy release distribution can be effectively modeled by just a narrow peak centered on the mean energy of reaction. However, if the intermediate is relatively long-lived, there is time for some of that energy to be redistributed among the internal modes of the intermediate. In the extreme case of full statistical redistribution, unimolecular decay theory predicts that the final translational energy release distribution can be modeled by a Boltzmann-like distribution of the form e to the minus e over e bar, where e bar is some mean energy. So here we have the experimental results for the bound, for the position distribution of the bound K plus I minus ion pairs at time delay of 30 microseconds following the end of the laser pulse. And here we have calculated distributions using a delta function energy release distribution and a Boltzmann-like energy release distribution. And as you can see, there is very good agreements between the experimental results and the model using the delta function distribution, which indicates that the CF3I minus intermediate is very short-lived. The next species we used was carbon tetrachloride, which upon collision with a Rydberg atom forms a Cl minus ion and a neutral CCl3. Now, the excess energy of this reaction is about 0.5 eV. So we perform the same analysis again, only this time you see better agreement with the Boltzmann-like distribution using a mean energy of about 100 MeV, from which we can conclude that in this case, the CCl4 minus intermediate is sufficiently long-lived to allow full statistical redistribution of the excess energy. So to test the full capabilities of this technique, we wanted to try a more general case. So we used BRCN. Now, upon collision with a Rydberg electron, it forms a BRCN minus intermediate, which dissociates to form a CN minus and a neutral bromine atom. And the excess energy of this reaction is about 0.2 eV. Now, unlike the previous two species, the only remaining vibrational mode that could be excited is the CN minus stretch mode. However, the energy spacing for that mode is 250 MeV, which is too large to be excited by the excess energy released by the dissociation. So what that means is that for all K plus CN minus bound states formed by this process, they will have a CN minus in the vibrational ground state. So what we can conclude from that is all the energy released from this reaction will either appear in translation of the fragments or it will appear in rotation of CN minus. Now, because the rotational constant of CN minus is relatively small, that means there is sufficient energy to excite many rotational states up to about J max equals 30. So when we attempted the same analysis with the previous species on BRCN, we see that we have a problem. We see that neither model agrees very well with the experimental results collected. When we look at the delta function, we can see that the agreement is very poor. So what we can conclude from that, at the very least, is that the BRCN intermediate must be very long-lived. However, we can also see that the full statistical distribution offers a very poor fit as well. However, this isn't unexpected because if we were going to have a Boltzmann-like distribution of translational energies, that would mean that all the other energy would have to go to rotation, so we'd have a preferential population of highly excited rotational states over less excited rotational states, which would be a very non-thermal distribution. So in order to try to investigate this, we produced new calculated distributions where we have translational energy release distributions that represent different amounts of rotational excitation. So we have a cold distribution in which nearly all of the energy appears in translation. We have an intermediate distribution, and we have a hot distribution in which nearly all the energy appears in rotation. So what we've seen from this is we do have strong agreements between the experiment and the intermediate distribution, which means that we have a broad superthermal distribution of rotationally excited states in the Cn- ion. Just to conclude, we see that we're able to use this model to effectively study the dynamics of dissociative electron attachment. In the future, we hope to rebuild this experiment to use strontium Rydberg atoms because we've noticed our group mates have discovered a higher yield of Rydberg atoms produced from strontium than with potassium. And this greater yield will allow us to better control our reactant parameters. For example, we can use an off-normal laser beam to produce velocity-selected Rydberg atoms. And finally, we have a wide variety of different potential targets from different lifetimes and a whole bunch of exotic decay modes that we like to use this method to probe. And with that, I thank you for your attention.